This is how we can approach questions where we have an inclined plane and a particle sat on it, and we want to work out either its acceleration or that it's in equilibrium and find a missing force. So let's read the question first. Particle is in equilibrium on a rough plane inclined at an angle such that tan alpha is equal to 4/3. Best thing to do as soon as you read that, just draw yourself a little triangle with your alpha, opposite over adjacent, and then you can recognise 3, 4, 5 triangle. Now you can find the exact values of sine and cos alpha. Just say to us finding alpha having some messy angle. Whenever we see a sine alpha, or we're going to use a sine alpha, we can immediately replace it with 4/5, and likewise for cos alpha. Okay, so if my pen would work. So let's start by drawing all of the forces on our diagram. First things first, we have the weight, 10G, and we want to resolve parallel and perpendicular to the plane. So I'm just going to colour code all of this. In fact, I'm going to use red as vertical, or perpendicular, sorry, and green as parallel. So my parallel component, parallel to the plane, will be 10G sine alpha. 10G times 4/5 is 8G. Similarly, the perpendicular component will be 10G cos alpha, 6G. If you're wondering how I knew that angle there was alpha, we have a right angle there, and this angle here we know must be 90 minus alpha. As that's 90, that must also be alpha. Okay, so we've resolved that one. Now we need to think, well, which way is friction acting in? It says we need to find the range of values of P, so let's try and find the biggest value possible of P. If P is as large as possible, friction must be stopping it sliding up the plane. So friction will be there. Any other forces I've not added yet? The normal reaction force. Called the normal reaction force because it's normal to the plane. Okay, so normal reaction force, we need to try and figure out what this is. Well, that's the force that stops our particle just falling straight through the plane. So it must equal any forces that are trying to drive it through the plane. In this case, 6G. But also, that force P is trying to push it into the plane. So there will be some component of P which is trying to force it through the plane as well. We'll need to find that. So again, you can justify to yourself that that is the angle alpha. We get 4/5 of P sine alpha times P. You see that we're using this little diagram a lot. And whilst we're resolving, we might as well resolve the adjacent one. That is 3/5 of P. Okay, so we know the normal reaction force must be stopping it falling through by opposing the 6G and the 4/5 P. Cool. Nearly there. Now what we can say is that our parallel forces, that force pushing up and those two forces, friction and HG pulling down the plane, must be equal. So because it's in equilibrium, we know the forces are balanced. Forces down the plane equal the forces up the plane. So we've got HG plus friction, and friction is the coefficient of friction times the normal reaction force. You know that if you're pushing something down and then trying to push it along, it's a lot harder. It seems to grip the surface a lot more. That's because the friction is equal to the coefficient of friction, which is a constant, multiplied by the normal reaction force. As you push it down, it becomes harder to slide. So we can replace that with a half of R. And now I can just expand and solve this. So I'm going to get 11G plus 2/5 p is equal to 3/5 of p. Therefore, p will equal, subtracting 2/5 of p, 1/5 times by the 5, 55g. We know the maximum possible value of p is 55g. But it did say the range, so is there a minimum value of p? Well, if we think about this, if left to its own devices and we didn't apply any force, this particle would start to slide down the plane. So we should consider, is there some minimum value of p that would stop it sliding down the plane? Well, now if the direction it's trying to move in changes, so will friction. Friction always tries to oppose the direction it's attempting to move in. So this won't change. P is still pushing it into the plane, but now friction is helping it. So we'll just do this calculation in blue. We know that the only force going down the plane now is 8g, and that must be equaled by 3/5 of p plus the friction force, which is still a half, 6g plus 4/5 of p. So you see, by changing the direction of the friction, we've effectively changed what side of the equation it's on. Okay, so on this, that's going to give us 3g. Bring it over here, leaves us with 5g. 3/5 of p plus 2/5 of p gives me p. So I can see that the minimum possible value of p is 5g if it's on the point of sliding down the plane. Therefore, the final answer to our question in this case is that p must be greater than or equal to 5g when it's in limiting equilibrium about to slide down the plane, but it cannot exceed 55g. At that point, it's in limiting equilibrium about to slide up the plane, and friction will be opposing that motion. Okay, just to colour code that so you can see where they came from. 5g, 55g. Okay, so key steps of that. First of all, little diagrams so that you know the exact values of sine alpha and cos alpha. Resolve all the forces in your diagram, being careful to realise that R may have more than one bit to it. Yes, it's resisting the weight pulling it through the plane, but it's also having to oppose P pushing it into the plane. You may have something similar. And then think about the direction of friction. Which direction would the particle be trying to move in? Friction will always oppose that. Then you can say, these forces are in equilibrium, so they must be equal to each other. Another occasion, you may have F equals ma if you know the particle is accelerating. Take the direction that it's trying to move in as positive. Those forces minus the opposing forces equals ma. You've turned it into an AS question.